Welcome to the deep dive. Today, we're looking at something truly audacious, where science fiction basically starts turning into real engineering blueprints.
Yeah, it's pretty exciting stuff.
We're talking about maybe humanity's biggest idea yet. The multi-generational starship, Chrysalis. This isn't just about, crossing space, it's about crossing centuries.
That's it, exactly. So for this deep dive, we're examining a hypothetical concept, a design proposing to send 2,400 people on a one-way trip,
One way.
a 400-year voyage to the nearest star system. I mean, the scale is so vast, the ship isn't just a vehicle, it has to be a whole self-sustaining world.
And what's really fascinating, what makes this worth digging into, is that it's not just some vague idea. This was a detailed concept, right? It actually won the 2025 Project Hyperion Design Competition.
It did, for interstellar architecture.
So it forces us to think about not just the physics, but the sociology of surviving for centuries out there.
The scope is just immense. And it's a great case study, really pushes the boundaries of our tech understanding and makes us ask these really deep questions about human endurance, societal continuity over 400 years.
Okay, so that's our goal today. Let's unpack the sheer scale, try to understand the engineering marvels needed, and then, get into the really profound human questions this whole idea raises. All right, let's start unpacking it. Beginning with the destination. You, the listener, imagine signing up for this 400-year, one-way mission. Where are these 2,400 people actually going?
The target is very specific, Proxima Centauri b. It's an Earth-sized exoplanet, and the exciting part is it might be in the habitable zone of its star, Proxima Centauri.
So the potential prize is huge, a habitable world.
Potentially, yes. For interstellar travel fans, it's kind of the holy grail right now.
Yeah.
A possible second Earth right next door, cosmically speaking.
Right next door is doing a lot of work there. How far are we talking?
Well, the whole Alpha Centauri system is 4.37 light years away. And if you try to picture that in miles or kilometers, it's about 25 trillion miles or 40 trillion kilometers. It's a number that's just hard to grasp.
Astronomical, literally. But, okay, here's the kicker. Why only 400 years? That sounds incredibly fast given the distance. Our fastest probes now would take, what, tens of thousands of years?
Exactly. That's the core engineering challenge, and it's where the revolutionary systems come in.
Yeah.
To get that travel time down to 400 years, Chrysalis needs continuous, sustained acceleration.
Right, not just a quick burn and coast.
No, it needs to reach a significant fraction of light speed, maybe 5, 10%.
And how on Earth, or rather, how in space, do they propose doing that?
The blueprints rely very heavily on something we haven't quite cracked yet on a large scale. Nuclear fusion propulsion.
Ah, fusion, the dream.
Pretty much.
Yeah.
Unlike chemical rockets or even nuclear fission, high-efficiency fusion drives could, theoretically, provide that constant thrust. They'd fuse light elements, generate enormous power, and just keep pushing the ship faster and faster.
So that's a key tech leap that shortens the journey from 50,000 years to 400.
That's the main one for propulsion, yes. It's a game changer, if we can achieve it.
That propulsion system alone is a monumental challenge. And then the ship itself, to last 4 centuries, it has to be more than just a ship. You mentioned the size.
Oh, the size is staggering. The design specs call for a vessel 36 miles long.
36 miles.
Yeah, longer than Manhattan Island. It needs to be that big because it has to be a completely self-contained world. No pit stops, no resupply for 400 years. Everything they need, they take with them or make on board.
Okay, how do you even build something like that? A flying city, basically, that holds together and keeps people alive for 4 centuries. Let's talk about the basic structure, the architecture.
It's quite innovative. The design uses a nested cylindrical approach. Imagine huge Russian nesting dolls, right? Massive sections inside each other, and these sections are designed to rotate.
Rotate along the main axis of the ship.
Exactly.
And that rotation, that's the answer to the big biological problem of long space flights, isn't it? Gravity.
Precisely. The rotation speed is carefully calculated to create artificial gravity through centrifugal force, mimicking Earth's gravity.
So about 1G.
Aiming for that, yes. And it's not just for comfort. It's absolutely critical for long-term health. Without it, you get bone density loss, muscle wasting, cardiovascular issues, stuff you just can't have happening over multiple generations.
Right. The kids born on board need to be able to function, potentially on a planet someday.
Exactly. They need to be physically robust. So that 1G is fundamental to the whole multi-generational plan.
So you've got this central spine, presumably non-rotating, with the engines and power.
Correct. A central core houses the really critical stuff. The fusion propulsion, the main power generation, the long-range communication stack.
And then around that, you have these rotating cylinders providing the ground and living space, like layers of an onion almost.
That's a good analogy. Concentric rotating layers surround this core. Each layer is dedicated to specific functions, specific biospheres, creating this layered, hopefully resilient internal world. The designers basically split this internal world into 3 main functional zones, kind of stacked outwards.
Okay, walk us through those layers. What does each one do? Where's the food grown? Where do people live?
All right, so the inner layers, closest to the central core, are the ecological foundation. This is where life support fundamentally happens. Think advanced vertical farms, big agricultural zones.
Growing all the food.
All the food, but also huge multi-level forest biomes, tropical, boreal. These are crucial for producing oxygen, recycling air, but also for psychological health. Imagine seeing green living things after decades in space.
Yeah, that would be vital.
This inner layer also has facilities for livestock and, importantly, zones dedicated to preserving genetic diversity, seed banks, DNA libraries, that sort of thing.
Hold on, if the forests and farms are in the inner layers, does that mean they experience slightly less than 1G because they're closer to the axis of rotation?
That's right. They might be calibrated for, say, 0.8 or 0.9 G, which could actually be beneficial for some types of agriculture, maybe easier resource management too. Clever design.
Okay, interesting. So moving outwards.
Moving outwards, you hit the middle layers. This is the community infrastructure. This is where the society lives and functions. Think large parks for recreation.
Parks. Inside a spaceship.
Expansive ones. Plus schools, universities, advanced hospitals, research labs, and crucially, vast libraries holding basically all of human knowledge digitally.
Wow. So the entire cultural and intellectual heart of this 400-year society is in this middle shell. The pressure to maintain all that education, research, culture across generations must be immense.
It's an unprecedented sociological experiment. Then finally you have the outer layers. These are for industry and housing.
Where people actually live day to day.
Exactly. Residential neighborhoods for the 2,400 people and their descendants. Alongside that, you've got industrial manufacturing they need to make replacement parts, tools, everything. Advanced recycling systems are key here, aiming for near total recovery of waste.
Nothing wasted.
Ideally, yes. Plus pharmaceutical production labs and huge warehouses for storing supplies. This outer layer is really designed for maximum self-sufficiency and closure.
The complexity is just mind-boggling. How does something this complex keep running for 4 centuries? We mentioned fusion power, but what about managing all these interconnected systems, the ecology, the resources, the people?
Well, beyond the fusion reactors providing, hopefully near limitless power, the long-term stability hinges on incredibly sophisticated artificial intelligence. AI systems are designed to be the ship's primary stewards.
Stewards? How so?
It's way beyond just environmental controls. The AI would constantly monitor and optimize everything, resource distribution, population trends, ecological stability within those biomes. Its job is to maintain long-term balance.
Wait, if the AI is managing population dynamics and resource allocation, that sounds like it has a huge amount of control, almost like a governing role over centuries. How do they deal with the ethics of that? A 400-year AI governor?
Yeah, the source material definitely acknowledges that's a massive challenge. The idea is the AI is a stabilizer, robust, incorruptible, designed to step in automatically if, say, an ecosystem starts to collapse or a critical system is about to fail.
So guardrails are built in.
The first generation would embed strict governance protocols, ethical boundaries. You're right, the sheer length of the mission means later generations have to trust this machine intelligence designed centuries before they were even born. It's a huge leap of faith. And just to connect back, right at the very core of the ship, there's a central shuttle bay. That's crucial for potential resource gathering, maybe from asteroids en route, and definitely for the final step, landing colonists when they arrive.
It's incredible engineering, but maybe the hardest system isn't the reactor or the AI, but the people. Let's shift to the human element. I mean, what kind of preparation do you need for a journey where you, your kids, their kids, none of you will ever see Earth again?
The training phase alone is almost unbelievable. The first generation, the ones choosing to go, would supposedly undergo 70 to 80 years of pre-launch training here on Earth.
70 to 80 years.
Living in completely isolated, self-contained environments. maybe deep under the ocean, or bases in Antarctica, places like that.
That's practically an entire lifetime spent practicing before the actual 400-year journey even starts. Is that even psychologically possible? It sounds incredibly demanding.
The thinking is it's necessary adaptation. It forces psychological adjustment to total confinement, to relying 100% on recycled resources,
Yep.
to being cut off from the rest of humanity. It's an extreme filter, really.
Yeah.
Only people who can thrive in that isolation would presumably make the final cut. But the truly unprecedented part, the biggest unknown, is the multi-generational society during the voyage.
Yeah.
It's a one-way ticket. Generations will be born to live their whole lives and die on board. Earth becomes history, something learned from archives. How do you maintain mental health, educational standards, social order, a sense of purpose for centuries, against cultural drift, against forgetting the mission? That's the huge question mark.
That idea of maintaining the mission goal across 15 generations or more.
Wow. Okay, let's fast forward. 400 years pass, they arrive. What's waiting for them at Proxima Centauri b?
The big hope, as we said, is it's Earth-sized and in the habitable zone. That implies liquid water might exist on the surface. That's the absolute baseline needed for colonization.
But it's not guaranteed.
Not at all. And this is where the huge risks come in. We have to stress the uncertainties. We simply don't know its atmosphere, what the surface is like, does it have a protective magnetic field?
And the star itself is a problem.
A big potential one. Proxima Centauri is a red dwarf star. They're known for throwing off powerful, violent stellar flares, much more frequently and intensely than our sun.
Which could be bad for an atmosphere. Very bad. Those flares could, over millions of years, strip away a planet's atmosphere, especially if the magnetic field is weak.
So they could travel 400 years just to find a barren, irradiated rock. The mission could fail right at the finish line. Does the design account for that possibility?
It tries to. The idea is the ship's advanced sensors and the onboard research facilities would be studying Proxima b intensely during the final decades of the approach, refining the data constantly.
So they'd know before they try to land.
Hopefully. If the planet looks too hostile, maybe the atmosphere is gone or radiation is too high, the ship itself is designed to be a long-term orbital habitat. They could potentially use it as a base to survey other planets in the Alpha Centauri system, or even just survive in orbit.
And if it is suitable.
Then those shuttles in the central core deploy. They ferry colonists down to the surface to begin setting up the first permanent human settlement outside our solar system.
The whole design is just brilliant, incredibly detailed, really inspiring. But let's bring it back to today. Chrysalis isn't lifting off anytime soon. What are the really big technological roadblocks?
Yeah, the sources are pretty upfront about this. There are at least 3 major technologies baked into the design that are currently unproven at this scale. They need decades, maybe even a century, more research.
Okay, what are they?
First, getting nuclear fusion power to work reliably, sustainably, and at the immense scale needed for that continuous 400-year thrust. We're making progress, but we're not there.
Right, that's hurdle number 1.
Second, the sheer mechanical challenge of building and maintaining those artificial gravity systems, these huge rotating structures. We've never built anything like them in space, ensuring they stay structurally sound, balanced, and mechanically reliable for centuries. The potential for metal fatigue, system failures, it's a huge engineering unknown.
Makes sense. And the third, probably the most vital for keeping everyone alive inside.
Exactly. Creating truly closed ecological systems. Designing, building, and proving an ecosystem that can reliably support thousands of people, processing all waste, generating all air, growing all food for 400 years with zero outside input. That's arguably the most complex biological and logistical challenge of the whole thing. We haven't even managed perfectly closed systems for long durations here on Earth yet.
So yeah, definitely not ready for construction tomorrow. But the value isn't just in building it now, is it?
Absolutely not. Even with these huge hurdles, the Chrysalis concept and others like it are incredibly valuable. They push research forward in critical areas. Sustainable habitats, better propulsion, advanced life support.
Technologies we'll need for any large-scale space exploration, even closer to home.
Exactly. It forces engineers to tackle problems relevant for Mars bases, lunar colonies, anything long duration.
Which brings us back to that core philosophical question embedded in this whole idea. Would you board Chrysalis, knowing it's a one-way ticket, total isolation, committing your descendants to this life? It's the ultimate pioneering sacrifice.
So wrapping it all up, what does Chrysalis represent? I think it embodies our capacity as humans to dream big, to conceive solutions to problems that seem almost impossible. It turns, wild science fiction into complex, solvable engineering puzzles.
A testament to ingenuity.
Yeah, and maybe a necessary blueprint if we're serious about long-term survival as a species, about thinking beyond just Earth.